Welcome to Advanced Quantum Chemistry and my first lecture on correlated wavefunction methods. I will start with a short recap of the Hartree-Fock approximation, and here the particular case of restricted Hartree-Fock, because almost all correlated wavefunction methods actually start with Hartree-Fock calculation. So what Hartree-Fock defines is that it is a one Slater determinant. We have one Slater determinant, and the orbitals in the Slater determinant are determined from the Hartree-Fock equations, and these orbitals give us the lowest Hartree-Fock energy. The spin orbitals are made as a product of a spatial orbital and the two spin function, either alpha or beta spin, and the spatial orbitals are generated by expanding them in a basis set, a set of known functions, which in most quantum chemical calculations are Gaussian type orbitals. And their linear combination of these basis functions gives us the spatial orbitals, where C, alpha I are the molecular orbital coefficients. And the molecular orbital coefficients are obtained from what is called the Rutherford's equations, which essentially is the Hartree-Fock equations for the case where the orbitals are expanded in the basis set. Now the spin orbitals if we have an n-electron system, the spin orbitals with the n lowest orbital energies, they are used in the Hartree-Fock determinant, and they are called occupied spin orbitals, and we normally use indices I, J, K, and L, and so forth for those. But solving the Hartree-Fock equations or solving Rutherford's equations gives many more spin orbitals than just those n, as we get as many spin orbitals as we have basis functions times 2 in the case of restricted Hartree-Fock. So they are psi n plus 1 plus psi 2m, and these spin orbitals are not used in the Hartree-Fock wave function, and they're called unoccupied, therefore, or virtual spin orbitals, and we typically use indices A, B, C, D for them. Now, with these extra virtual unoccupied spin orbitals, we also, of course, can make many more Slater determinants by using those orbitals instead of what we call the occupied orbitals, the ones which are used for the Hartree-Fock determinant. And of course, we can make Slater determinants where we have some of the spin orbitals which are used in the Hartree-Fock Slater determinant and some of these unoccupied orbitals. And in order to get some order in all these many Slater determinants which one can make from a set of 2m spin orbitals, one designates them typically by referring to how they differ from the Hartree-Fock determinant. For example, if we replace one spin orbital, one of the occupied spin orbitals in the Hartree-Fock determinant by a virtual orbital, here for example, here we have psi a in the place where there used to be an occupied orbital in the Hartree-Fock determinant. So if we replace one occupied orbital with a virtual spin orbital, then we call this kind of Slater determinants single excited Slater determinants. And as I already mentioned before in my lectures about Hartree-Fock theory, in particular about the Bremner theorem, this is in a way is an unfortunate name, because one should not immediately think about excited states of the system. This is not a very good description of an excited state. So just let's think about that these are some extra Slater determinants where I have replaced one occupied orbital with one virtual orbital. So this notation is trying to indicate which occupied orbital was replaced by what virtual orbital. Of course, we can do that not only once, we can do it twice. So here we have two different occupied orbitals, I and j, we have replaced by two virtual orbitals, A and B, and we can do it 3 times, etc., etc. And we can do it actually up to n times, because for an n-electron system, we have n spin orbitals in any Slater determinant. Now, what can we use these extra Slater determinants for? Well, all these Slater determinants which we can form from a set of spin orbitals. So if we start out with a basis set with m basis functions, giving us then m spatial orbitals, and therefore 2 times m spin orbitals, then we can make quite a lot of Slater determinants. The set of all these Slater determinants, including the hard-to-fuck Slater determinant, forms then what is called a many electron basis set. And in the same way as we could expand the spatial orbitals in a one electron basis set, we can now expand our n electron wave function in this many electron basis set. And that is here, so we can expand our unknown many electron wave function, the solution to the Schrödinger equation. We can write it as a linear combination of all these Slater determinants, starting with hard-to-fuck, single excited, double excited, and so forth, up to n-tuple excited determinants if we have an n-electron system. This expansion of the unknown many electron wave function will be exact if our one electron basis set is complete. Unfortunately, as we discussed in previously, a complete basis set is infinitely large, which then of course also would lead to an infinite number of Slater determinants. So in practical calculations we will never be able to do that. We have to constrain ourselves to a finite basis set. Nevertheless, even in the case of a finite basis set, when we generate all the Slater determinants which we can from this basis set, and then write our many electron wave function as this linear combination of all these Slater determinants, then we will call this wave function as the exact wave function for the given basis set. Of course, we have to determine the values of the coefficients, but I'll come back to that in a few slides. Now, another important term which one uses very often when one talks about correlated wave function methods is the expression correlation energy. And in principle, the correlation energy is the difference between the exact energy, meaning the exact solution to the Schrödinger equation, and the hard-to-fuck energy in the limit of a complete basis set. But as I said, just that, we'll never be able to do a calculation in the limit of a complete basis set, because that would be an infinite basis set. So for a finite basis set, we can also define a correlation energy as being the energy calculated with the wave function, which includes all Slater determinants possible in this finite basis set, minus the hard-to-fuck energy calculated in this basis set. And then, of course, when we make the basis set larger and larger, this correlation energy will converge slowly to the exact correlation energy. Now, the big question is, how can we determine the values of these coefficients so that we get the exact, or an wave function which is as close as possible to the exact wave function? There are essentially 3 different ways how we can determine those coefficients. One is we just use the variation principle, which means we calculate the energy as an expectation value of this wave function, and then we determine the coefficients in such a way that the energy becomes a minimum, meaning we take the derivatives of the energy with the coefficients and again get a set of equations which we can solve. There are 2 methods which take this approach. One is called configuration interaction with the acronym CI, and the other one is multi-configurational self-consistent field, or MCSCF, and we will talk about those later. Another approach is using perturbation theory, and here for the problem of electron correlation, it's a particular Müller-Blessed perturbation theory, which, by the way, was developed at our university, to be more precise, at the physics department, which is nowadays called the Niels Bohr Institute, by Christian Möller and his postdoc. And finally, we'll look at couple cluster theory, where one obtains the coefficients by projecting the Schrödinger equation against some Slater determinants. In the following 3 lectures, I will discuss each of these 3 ways, meaning each of these type of correlated wave function methods.